Hello and welcome to the Stardog Academy training on working with text. I'm Jaroslav Pullman. To let you know a bit more about me, I'm a solutions architect at Stardog and passionate about solving problems with customers. In the past 20 years, I've engineered solutions for various domains spanning from interactive speech applications, text processing, IoT systems, and a plethora of semantic web services. Today, I'm going to walk you through working with text. In this training session, you will learn how to configure and use the full text search feature of Stardog, to understand the options for integrating unstructured data, and to leverage and extend Stardog's text processing feature. Let's get started. This section is about a full text search in Stardog. The full text search over string literals in RDF graphs operates on attribute values, objects of a particular data type. These are by default plain strings or strings with a language tag. Text indexing and search is based on Apache Lucene and transparently managed by Stardog. The index is updated on database creation, optimization, and transactions modifying the database. It seamlessly integrates with SPARQL and is also available via Java and HTTP interfaces. The full text search is disabled by default. You have to enable it by setting the database configuration property search.enabled to true, either at database creation or at any time afterwards. The database has to be offline in order to change this property. Looking at an example in Stardog Studio, please offline the database first, enable the full text search, save the updated configuration, and set the database online again. These are the corresponding commands to enable full text search via Stardog's command line interface. A number of configuration properties exist to customize the full text search functionality. Corresponding property names start with the prefix search. The following properties define the scope for indexing and search. The property search index data types enumerates data types that should be indexed, for example XML schema string or derived data types. The property search index properties excluded is a blacklisting of attributes to be ignored. The property search index stop words allows you to redefine a set of frequent words that are usually excluded from indexing, such as are, the, with. For example, depending on context, the preposition at may refer to the language code of Austria, AT, that should be retained by constraining the set of stop words. And these properties modify the search behavior. The property search default query operator indicates the default Boolean operator connecting the search terms. The default operator O requires at least one of the terms to match. Consider changing it to AND to enforce searching for all query terms. The property search wildcard search enabled will let you search for terms with an unknown beginning. Please note that searches with a leading wildcard require an expensive index scan and are generally slower. SPARQL graph queries require simple literals, that is, strings without a data type RI or language tag, to be identical in order to match. Inexact matches involving any kind of normalization or comparison logic are expressed via a filter clause and corresponding functions such as contains or regex. String literals are treated as an opaque content, so the filter condition has to be applied to all values selected by the graph pattern and are inherently inefficient. In contrast, the Lucene full text index exploits the internal structure of string literals to directly retrieve values matching the query expression. This is supplied as a literal object. It is constant to Stardog's custom predicate text match that in turn binds query results to its subject variable. Optionally, you may retrieve or enforce the matching score of full text search results by supplying a parameter list to the text match predicate. The score expresses the relevance of the result computed by a ranking function. The ranking function applied is BM25. BM stands for best matching, a modern variant of function used in document retrieval based on term frequency TF and inverse document frequency IDF. Term frequency represents the number of times a term occurs in a document. Inverse document frequency is the inverse function of the number of documents in which it occurs and is higher with less frequent terms. Lucene supports a range of modifiers to enhance query terms. For example, enabling a fuzzy search, emphasizing boosting a term, or expressing more complex expressions via groups and Boolean operators to enforce via AND or prohibit via NOT the occurrence of a term. The text match service extends the functionality of the text match predicate. Most importantly, it accepts dynamic query expressions retrieved from the data by the parameter query, whereas the predicate supports only constant query strings. It further defines a number of parameters, for example to paginate the resultant literals via offset and limit parameters, to retrieve the plain results via parameter result, an HTML text fragment with matches highlighted via parameter highlight, to access the underlying Lucene query via parameter parsed query, or an explanation about computing the score via parameter explanation. Please note the IRI of the text match, predicate, and text match service differ in the namespaces. This sample SPARQL query demonstrates the use of the text match service, a dynamic query expression, and a graph matching based on its results. First, name of artists related to albums are selected. Each artist name will be used as an input to a search query in the full text index. The text search results are bound to the variable other artist and used to look up their albums in the database. Lucene analyzers process text for indexing and search. It's crucial the same logic is applied at both phases, ensuring consistency. Each analyzer contains a purposeful combination of tokenizers and filters. An analyzer may split up the input on white spaces, apply tokenization, or remove stop words, normalize the tokens by converting in the lowercase, etc., applying filtering. Stardog leverages the standard Lucene analyzer by default. This may be configured via properties introduced earlier. Alternatively, you may consider implementing an own search analyzer. An example project is available on GitHub repository. The custom analyzer would extend the Lucene analyzer class and be exposed to Stardog via an analyzer factory. The analyzer factory class is registered via Java Service Provider Interface mechanism with Stardog. Let's proceed with a quick demo of the full text search functionality. First, we need to enable it on database, offlining the database, enabling the search, saving the configuration, and onlining database again. This is a classical SPARQL query for inexact matches, looking for a substring within the album name to contain the token let, the term let, and the equivalent using the text match predicate. Now, list comprising of the name, which is going to be the result variable, and the score is supplied as a subject of the text match predicate. This is the example of text match service being used, where the query is supplied as a constant. A particular threshold is set up. The results are limited to 10 literals, literal values. For example, Lucene query is being bound to the parse query variable. And this is an example of full text query where the query itself is being supplied by a graph matching, so from the artist being bound by the artist name, and the results are used to identify albums by other artists where there's a condition the artist should be different. This concludes the section on full text search. This section is about text processing in Stardog. Stardog supports storage and processing of unstructured content via a feature called bytes. This is an acronym for blob indexing and text enrichment with semantics. Bytes accepts a wide range of document formats such as downloaded web pages, Microsoft Word or PDF documents. It may extract plain text and related facts when the document is checked in. By default, these facts comprise document metadata such as format or size and named entities such as organizations or places that were recognized in the document and optionally linked to graph resources. This default processing may further be customized or entirely substituted by custom components called extractors. Facts related to a document are held within a dedicated document graph. Subsequent updates to a document may either replace or incrementally augment the document graph. Stardog may optionally persist the documents within the local file system or in cloud storage such as Amazon S3. For sake of consistency, Stardog acts as a gatekeeper and prevents a direct manipulation of the stored documents. Various APIs exist to manage the lifecycle of those documents, for example via the command line, Java, or Python. This architecture diagram outlines the processing flow of unstructured content in Stardog. In contrast to loading native RDF data or translating structured content via virtual graph mappings, the ingestion of unstructured content necessarily involves a series of processing steps, each implemented by an extractor component. The metadata extractor collects descriptive attributes such as size or format by analyzing the file and by introspecting the metadata supplied within the document. The text extractors are responsible for extracting plain text content out of the potentially binary, formatted, and otherwise enriched document. Any subsequent RDF extractor operates on this input in order to generate facts. It is RDF statements that are ingested into the document graph. Configuration properties related to document processing have the prefix docs in the name and may be updated at any time without offlining the database. The properties docs default text extractors and RDF extractors accept a list of comma-separated extractor names that apply by default. It is when no extractor is selected at processing time. You may further configure the storage protocol and location via the properties docs file system URI and docs path respectively. Setting the format to none will disable the document persistence and thus prevent creating copies of potentially sensitive content. The property docs OpenNLP models path indicates a directory relative to Stardog home that contains the models for natural language processing and any related files such as entity dictionaries for linking. Entity linking based on database contents and a full text search for documents requires the text search option to be enabled. The Stardog command group doc serves the lifecycle operations on documents. It is to create, respectively check them in via the docput command. You may override the default settings and indicate specific text or RDF extractors to be applied and whether any previously extracted text should be retained or dropped, which is the default behavior. The docget command will retrieve the document from the storage by file name, optionally creating a copy using the alias. You may delete a specified or all documents in a storage via the docdelete command. Docount returns the number of persisted documents and the docreindex command will update, it is replaced, the asserted facts by applying the default or specified extractors. This is an example of a full text search via the text match predicate applied on document content. It retrieves the IRI of any matching document along with the statements asserted in the document graph. Please note the document and its graph share the same IRI, so you may attach corresponding annotations such as provenance or editorial notes to the document graph. Extractors were already introduced as the extensible means to process unstructured content in Stardog. It is to extract plain text, document metadata, or related facts. The built-in TextExtractor is based on the Apache TK framework and used to extract text and document metadata by default. On top, named entity recognition and linking is supported out of the box by the extractors entities, linker, and dictionary. The entities extractor detects mentions of named entities in the text and generates some basic assertions, such as entity type. For the purpose of name entity recognition, Stardog leverages the Apache OpenNLP framework. Corresponding language models should be placed in directory indicated by the property docs OpenNLP models path. The numerous models for 105 series are still compatible with more recent OpenNLP versions. Stardog loads the models based on a naming convention, expecting at least one tokenizer, sentence detector, and at least one name finder model for the actual entity extraction. The name finder models are either statistical, pre-trained on a sample corpus with a file extension bin, or based on an explicit listing of entity names with a file extension dict. The linker extractor augments the entities extractor by linking identified entities to resources present in the current database. The entity mention is matched to the local name and name attributes of RDF resources, such as RDFS label, for-of name, and so far. Only entities that were successfully linked by the predicate DCT references are returned by this extractor. Similar to linker extractor, the dictionary extractor links named entities to predefined resources, but it leverages a user-supplied dictionary instead of similar graph nodes. A dictionary is a proprietary file with the extension linker located in a models directory. It maps each entity mention to at least one IRI, it is to the target resource. This example class generates a dictionary linker that maps company names, it is entity mentions, to the Wikipedia resources. You may adapt it to cover entities of your domain. This SPARQL query demonstrates a search for named entities upon document graphs. Predicate docs has entity links the document to ad hoc entities introduced by the entities extractor. These are in turn linked to third-party resources by the DCT references relation. In contrast to the previous example, the entity extractor service operates upon any text object supplied by the parameter docstext, including remote sources such as SPARQL endpoints and virtual graphs. The extracted entity mentions are exposed by the parameter docsMention. When present, the parameter docs entity is bound to entity IRIs implicitly retrieved by the linker extractor or the dictionary extractor when selected by the docsMode parameter. Let's look at the options for extending the bytes functionality, considering a custom TextExtractor first. It implements the TextExtractor interface and exposes the content retrieved from the document path via the standard reader class. In this particular example, the extractor delegates the task of document parsing to Apache TK and logs the result. If you need to extend bytes but you would like to retain its document handling API, consider implementing a custom RDFExtractor to integrate this feature with an external service for natural language processing. Example of a successfully integrated software in a life science domain is the Cyber server Termite that acts as an extraction and linking of named entities such as genes, drugs, or diseases. Further, as part of a prototype, we integrated a popular Python framework Spacy to demonstrate extraction of management change events from web media. As shown in the code snippet on the left, a custom RDFExtractor exposes a set of statements gathered from text input by implementing the extract from text method. The overall process of entity extraction and linking will be customized at any individual phase of document parsing, mention processing, candidate generation, feature generation, candidate ranking, and selection. The example document parser on the right is responsible for extracting tokens along with their type from the bread annotation format retrieved from an external SPACY-based entity processor. Let's look at some examples how to configure and use the text processing feature in Stardog. First, let us check the prerequisites and ensure the language model directory has been populated and configured. We'll create a folder within Stardog Home, for example called models-en, for the English language models and download the appropriate models. This is a sentence detector, a tokenizer, and a number of name finder models for recognition of entities of particular type like date, location, or organizations. For an entity type, you may either download a corresponding name finder from the OpenNLP website or train a custom name finder model. Once the model directory is set up, please configure it with your database and restart the server. For linking and text search on documents, the text search option should be configured as well. The following steps are based on this example Word document copied from Wikipedia. It contains two named entity mentions, the fictional Acme Corporation and Warner Brothers Studios, that are safely recognized by the OpenNLP organization name finder. Now let's check in the document using the default settings via the doc_put command. This query will find the example document by means of a full-text search. It retrieves the document IRI and facts, it is metadata, asserted by the default TK-extractor. With the OpenNLP models in place, we'll test the basic entities extractor, replacing the previous document description. Please note the name entities of type organization that were recognized and linked to the document via the docs has entity predicate. An initial run of the linker extractor will fail since no other data was yet loaded into the database. Please note there are no name entities in the result set. Now let us populate a database using a federated query of DBpedia resources. The describe query confirms the resources were successfully loaded. When executed again, the linker extractor was now able to compare and link the name entities to resources in the graph. The dictionary extractor will link and retrieve entities covered by a custom linker file that was deployed to the model directory. This particular one was built using the following code with an entry for Acme Corporation only. Acme Corporation is therefore the only named entity that shows up in the result. And this is an example of applying the same dictionary extractor via the entity extractor service to text objects in the graph. This final example demonstrates a custom RDFExtractor that invokes an external named entity processor written in Python. This is a simple web service that encapsulates the space library, processes the input supplied by the text parameter, and returns entity annotations in the bread standoff format. There is an annotation ID in the first column, followed by the entity type and index boundaries of the entity mention. The format was extended by an optional entity IRI for linking in the last column. The same text is now ingested via the Bytes API using the custom linking spaCy entity extractor that consumes the previously shown web service. Both named entities, Scrooge McDuck and Duckburg Credit Union, were successfully extracted and linked. This demo concludes the section on text processing in Stardog. Please find here some recommended resources on text processing in Stardog. These are a reference to the documentation of Bytes, blog posts by its developer Pedro Oliveira, and code examples on GitHub. That concludes the Stardog Academy training on working with text. We've reviewed how to configure and use the full text search feature of Stardog, understand the options for integrating unstructured data, and how to leverage and extend Stardog's text processing feature. Thanks for following along. If you have any questions, please review our frequently asked question page or head to docs.stardog.com for additional information.